Okay, so we're doing a proof by contradiction problem from the midterm. We're going to show that for any rational number and any irrational number, if the rational number is not 0, then the product is irrational. The first thing we want to do is put this in a little bit more mathematical notation, and that'll make it easier for us when we need to take the negation of this as part of our proof by contradiction. It'll be more clear to see what the negation really is. So let's start with that. So we're saying that for any rational number, we'll just call that x, and for any irrational number, we'll call that one y. If x is not 0, so x is the rational number, so if the rational number is not 0, that implies that the product, x and y, is irrational, is not a rational number. So, okay, let's get started with our proof then, and we'll see how we're going to come back to that. So, this is our theorem, and then we're going to say proof by contradiction. Okay, so first thing we do, of course, is we're going to assume the opposite of what we're going to try to show. So we say assume not, that is, assume. Now, at this point, we need the negation of our theorem here. So we're going to need to review a couple negation rules here. So the first thing is we have these for-alls, and we're going to have to negate that. So we're going to make a note to ourselves up here that the negation of some universally quantified statement about x, so we have for all x is the member of some set, and then some predicate about x. So the negation of this whole thing is that there exists an x that is a member of that set, but it is not the case that predicate of x is true. Okay, so a couple of things to notice here. One is that this set membership does not change. What does change, I'll mark in green, is that the for all changes to an exists, and then the predicate becomes the negation of the predicate. Okay, so we're going to say here, assume that there exists an x that is still rational, and there exists a y that is still irrational. And now we need to take the negation of this part of it. So we're going to come over here and remind ourselves how we take the negation of a implication. So not P implies Q, remember, is the same as P and not Q. So this is our P part here, and this is our Q part here. So we're going to say that x is still not equal to 0, but it is the case now, we're going to say not Q. So we were saying that the product xy is irrational. Now we're going to say that the product xy is rational. So that's the opposite of that one. Okay, so what we know about this then is that x is rational and y, and the product xy is rational. So we're going to have to use our definition of rational to plug in here. Now, we don't have a definition that we could plug in for irrational numbers. They're not like odd or even or rational where we have these definitions we can plug in. So we're just going to have to leave y as is. But let's go ahead and plug in the x and the product xy. We're going to pause, and then I'll see you in part 2.